Okay, my name is Philip Ernst. I'm from Imperial College London, and I'll be chairing this session. So our first speaker is Sara Mazzonetto from University of Lorraine, Nancy, and she'll be speaking about the number of crossings, statistics, and local dimension and local time estimation for sticky diffusions. Thank you.
Thank you very much for the introduction. Thank you very much to the organizers of the workshop for the invitation and the possibility of talking about my work. So what I will talk about are some work in progress with Alexis Anagnostakis, who is a postdoc in Grenoble. And we started working some time ago, not as much time ago, about local time estimation for sticky diffusions. And some of you maybe already heard some part of the results I'm talking about. So I hope that will be understandable for everybody, also the people who didn't see before, because I will start from the beginning. And today I will present a baby step more towards understanding of what happens in a certain class of statistics for local time approximation. So I will start talking about what is sticky Brownian motion, reminding how it was introduced and why, in particular sticky reflected. And then I will go to talking about local time estimation and a particular estimator, which is well known. It is the number of crossing. So you count the number of times you cross a certain point. So this talk is completely one-dimensional. So, no, not that much. So, as I said, I will start reintroducing the process. Then I will talk about the question we ask ourselves, and then I will discuss about the results existing and the new step that we did. Finally, it's an application, but theoretical, to see how one could use this results to estimate parameters. So what is sticky Brownian motion? Well, let's start with a picture, just like that, in such a way that before the definition, you already have an image that you can keep with you if you have not seen it already. So it is Brownian motion everywhere outside 0, and at 0, it is slowed down. We will see what we mean with that. Many of you are familiar with it, but let's see. So that's a simulation of a sample path of sticky Brownian motion done with a method introduced during Alexis' PhD thesis for simulating this kind of process and also diffusions. Okay, so up, no, not that much. Yeah, here it is. So for introducing more formally the process, I will go through an historical overview. And I like very much the paper of Pesquer of 2015, in which he talks about the whole history from Brown to Feller, this like presenting how reflected sticky Brownian motion was introduced when Feller was trying to characterize all possible boundary behaviors at 0 when you have reflected Brownian motion, and you have he looked through analysis. So he looked at the infinitesimal generator of the process, so we can think of the second derivative, the Laplacian, and then he would say, okay, what are the possible behaviors at 0 of the process? And you will see that at a certain point, a possible condition would pop up. And at first, I was not there. I can only say what others say, what they understood. He didn't immediately think of what. So that is working very bad right now. It was working better, so we'll change. Then, so he would not see immediately what this condition would do. So why this was an astonishing condition? Because you have the second derivative of a function. So you have the Laplacian as infinitesimal generator, and then you have the second derivative at 0 plus, because we are on 0 plus infinity, related to the first derivative through a parameter, which is then from now on, it's called the stickiness parameter. And then one has to understand what does this process do when you change. Oh, here it is. And then there was already the idea that one-dimensional diffusions, already from the 30s, in between the 30s and the 50s, Feller got already the idea that one-dimensional diffusion could then be described through the infinitesimal generator with respect to what is now called scale function and speed measure. But there was also the idea that one could construct one-dimensional diffusion from, so trajectorically, really a construction from time change of Brownian motion, and then you apply a function which changes the space of trajectories. And the construction for sticky reflected Brownian motion was then written properly by Ito and McKean, which would construct sticky reflected Brownian motion as a time change of reflected Brownian motion. And this time change is the time change coming from the local time of the reflected Brownian motion at 0. We have stickiness at 0, as we see here. So we are on the Lian line, a positive semi-axis. And here it is the local time. So the time change would have this inverse related to the local time of the reflected Brownian motion, which would mean that gamma t is smaller than t. Then the process is slowed down. In this sense, then, sticky Brownian motion is a Brownian motion which is slowed down at 0. And this makes that you spend a positive amount of time. So the Lebesgue measure of the time you spend at 0 is positive. And actually, you would like to know more. You would like to relate this positive amount of time, which we can say the occupation time of 0 of the process, you would like to relate it to local time in some sense, because it's easier. And this is a key element of what is the pathwise description that I will use later, and that allows us to find approximation of the stickiness parameter through local time approximation and occupation time approximation. So I told you all the talk, I can go, but let's see a little bit more. So I said that I will not talk about reflected Brownian motion, sticky reflected Brownian motion until the end. And indeed, now I pass to sticky Brownian motion and not sticky reflected. So the image I showed you, it is not sticky reflected. It was on the real line. And then at 0, there was this sticky threshold. And so the construction, which was already older somehow in the spirit, was the one from characterizing the process through the generator in the general form, which comes from Feller, which is related to the derivative with respect to the scale function and the speed measure. I won't give the definition of this. If you need, I have them, of course, but I will just remind that what it was said already from Feller or Ito or McKean, you have a one-dimensional diffusion, so a strong Markov process with continuous trajectories, and it can be obtained by a Brownian motion run by a new clock and a function which sends it to a new path space. Here, the path space doesn't change, so it's always the same. It is the identity, but the measure, the speed measure here, it is the one which changes the clock of the Brownian motion. It is the same that I introduced before, except for a factor 2. Which was just a fake. It's because we want to have that when we take the absolute value of a sticky Brownian motion, we get a reflected Brownian motion with the same parameter. And that's only the fact why sometimes you will get a factor 1/2 that appears. So just to complete the picture from the infinitesimal generator, although I will not use it because I will use the pathwise characterization, then the boundary condition in the case of two-sided sticky Brownian motion and not sticky reflected is the fact that you get a jump in the first derivative with respect to the left and to the right, which is proportional to the second derivative. And that's it. Okay, so we now go to the pathwise characterization. So one thing I should have said, and I didn't write it, so I will do it now, is that as far as I could reconstruct sticky Brownian motion in the way not reflected, it can, of course, be said that it comes from Feller, but we can also say that it was considered from Amir, where in 91, when he looked at random walk, which would spend a certain amount of time at 0, and then he showed that there would be convergence to sticky Brownian motion. And in this sense, he also constructed the classical, let's say now classical construction that I showed you before for sticky Brownian motion. So since I didn't mention, I have better do that. So for the pathwise characterization, in the sense of looking at a system of stochastic differential equation that the process solves, I wrote both for sticky reflected and sticky Brownian motion. So this is the one for sticky Brownian motion, and this one for sticky reflected. So for the historical reason that I just introduced, I think the first characterization was for sticky reflected Brownian motion. And there are several results. I cite some, but they're not as many on this sense at the time. So Shitashvili in 89 would try to prove that, there is no strong solution, which was something which was conjectured by Scarhod. And then there was also a different equation that would come into play, only one equation in which you would replace the local time by the occupation time here. And then it was proven that the expression are equivalent very recently. And also it was proven that there is no strong, solution by uniqueness in law holds very recently in 2 independent works. So Bass would consider semi-martingale with a certain speed measure and would prove that it would characterize the SD and so on, and with different techniques on stochastic analysis, Engelbert Tepesky described this equation, where you would have a Brownian motion outside 0, and then you have the reflection, which is given by the local time, but you still have here that the information that the occupation time is proportional to the local time, which is what this is what I told you before, that it will be very good for us in the purpose of estimating the parameter, that this means that you can approximate occupation time differently in the local time and do estimation. So from now on, we look at this equation where you have occupation time proportional to local time and this. So sticky Brownian motion. You do not have reflection anymore. You do not have anymore the local time which pushes you up in this expression. So, okay. What we are going to change now, after the introduction to the process, we will go to the problem of estimation and the number of crossing. So the question is, you have a process observed up to a certain time that we fix at t here. We fix the time 1, t equal to 1. You observe it at discrete times. We take them equally spaced. And you ask, in the case of sticky Brownian motion, for instance, if you can estimate the parameter. That's an old question. I mean, we can also, the question here, it's an old question. It's not particular for sticky Brownian motion, nor when I will talk about a sticky diffusion. It is also for sticky diffusion, for a standard diffusion. I will look, for instance, for some second at the solution to a stochastic differential equation with homogeneous coefficient. sigma positive, all the good hypotheses. I just want to talk about estimation. Actually, I will take sigma very regular at some point. And what we look at here is, okay, let's take also this R. So the number of crossing estimator was already used, or other kind of approximation of local time were already used to trying to estimate non-parametric estimation of the diffusion coefficient at fixed time. And this goes back to the 80s, 90s, end of the 80s, beginning of the 90s. For instance, I will cite the results where you already study local time approximation for estimating the function sigma. And why would you do that with local time? Because when you look if a sigma can change, can evolve, that when you want to know the value at a certain point x, so as function, that you will look at the behavior just around x. And so the local time comes into play. One would like to take occupation time, but for Brownian diffusion, the time you spend at a point is 0. But the local time, it is the infinitesimal time you pass around, and therefore that's very intuitive. Then you can try to estimate that. So there are some results for certain statistics for non-recurrent processes, but the non-recurrent processes we look at, they are not, they don't follow in this setting. So they are singular diffusion with respect to the Brownian motion, and therefore we have to study somehow them in different ways. When we have a drift that allows for ergodicity, for instance, we can look at problem like in long time and other results with classical methods. And here we look at somehow classical methods based on semi-martingale for trying to estimate the local time. So the key point, I've already said it, I repeat myself very much, but for the key point here, for the estimator of the stickiness parameter, is the only part of the information we have that contains the stickiness parameter. And therefore, the fact that the process spends a positive time at 0, occupation time, and that this time is related to local time. So one idea is to look at approximation of local time. So I said that I've already presented the result that I will recall later. And the result I will recall later, it's a result for a statistic which will contain only one at every time you make the sum of a function of one observation. And we wanted to pass through considering the classical statistics, which is the one of, for instance, number of crossing, because that's the local time. You look at what happens around, and therefore I will recite the problem, or we recite the result, but that's what is the result. When you can see the increments, when you can see from one side and the other. And so I will reinsert everything in the context of, on the historical context of the classical estimation of number of crossing by telling that there are really several approaches that were used, which give results that, as far as I understand, were not known to one another in different communities. So from the dates, I will see work of Gickman as a work in 57. There's a work that consider number of crossing for Brownian motion. So and prove that the rescaled the number of crossings, so not this, but the rescaled number of crossing converges to some quantities that can be identified to be the law of the local time. So it is a convergence in law done through analytical results, which gives the first result on the number of crossings. And in France, I would say, in the 89-91, there will be several authors who look at the question for Brownian motion and Brownian diffusion and would provide different proofs for the same result. They would, okay, here it's a typo because I fixed time equal to t, but they would go towards proving results functional convergence theorems, not only just for fixed T, convergence in probability or convergence in law. So they would improve to convergence in probability uniformly in time. So that would be a functional convergence in the Skorokod space, and they will prove the convergence for the renormalized number of crossing. So I will cite other works in the next slide, which would go towards the speed of convergence as well. Let me first say why. Maybe you see it immediately, but why at first there is an n to the 1/2, where we are looking at the observation which are close to 0, right? And so you can think of the analogy also with the random walk, in the sense that you would have not all the observation that will give you a contribution in the statistics, but the order of square root of n. And therefore, when you renormalize, you will get this kind of convergence. And if we go further, then this will not surprise you, the speed of n to the 1/4 in the classical case. So one remark that I already gave, it is the fact that it doesn't suffice a convergence in law is also related to what we want to do. We want to consider a ratio of convergence of two parts. Let's say we have convergence of a statistics to the local time times a constant, which depends on the parameter, and converges to the local time to another constant, which possibly doesn't depend on the parameter or depends in such a way that they cancel. Well, you want that the local time is the same. If the local time is not the same, you cannot conclude anything. And in particular, you do not want just convergence in law. You want a convergence which is stronger. Convergence in probability is fine. But if you must have something else, that you need one convergence in probability and the other one stably in law. That's why the results that are given then for convergence are are stronger than just the convergence in law or convergence in probability. Although I will start writing convergence in law. But what I should then say is that somehow this talk shouldn't take place, because in '89, for sticky Brownian motion, it was proven that this statistic, which is the number of crossing, would converge in law to a discrete random variable in the case of sticky Brownian motion. And then you tell me, but then why are you presenting everything? Well, it is true, there is a result which tells that you have convergence in law towards a discrete random variable, and that's this is again analytical, same kind of approaches which are different than one that you look at, which gives convergence in law to a discrete random variable whose the probability, so it is probability that the random variable is equal to a certain value is given by quantities which are related to the Laplace transform. So yeah, the Laplace transform of the law, which is remarkable. We have not yet looked through every details yet. That's quite complicated. Sometimes the works are not available. We do not have this. Thanks to Andrei Pilipenko, I could get to a paper of Portenko, which was summarizing all these results I talked about. But then what we were trying to do also before to know, yeah. Yes. Yes. It's for Brownian motion. Yes. And we actually want to analyze what happens for sticky Brownian motion. And that's why I tell why am I talking about that, since there is this result. But actually, yeah. And there also seems to be a type, the T should be 1. Yes, the T should be 1. Yes, I've said it. Yes, because I fixed T equal to 1. But that's true that all the results that you will take, you can see them in convergence as in the spherical space as yeah, it's functional convergences. But I simplified because we are looking at a fixed time for the estimation. So I will do it. Yeah.
Yeah. So you mentioned something about it, but the law of Z is known explicitly.
So the Laplace transform.
That's
Mhm.
Richiamento por tempo paper, where can we find it? This richiamento for tempo paper, where is it?
In which journal? So I know in which journal? Yes,
It exists.
yeah, it exists. Yeah, it exists. So yes,
Actually, the
so-
first name is spelled, actually. The last name of the man is Efimenko, E-F-I instead of Y-E.
I'm sorry, I actually copied it from Portenko review of 93. So I'm sorry if I misprinted. So I should take this. So what I wanted to look at is to more general statistics, including the number of crossing statistics. So all this problem is a special case of what we wanted to look at. So we wanted to look at two statistics, which yes, would take the observation at the spot, let's say a spot observation, but we'll also look at crossing, in particular at increments. So it's a very complicated formula. I would go through that later. So it is what I was telling you, that this kind of statistics were already studied in the 90s, 80s, and 90s in order, for instance, to give estimation of this kind of coefficients. And that's a remarkable work of Franz Wien, for instance, for coefficients which are regular. So I'm used to work with singular diffusion in the sense of threshold, like skew Brownian motion, oscillating Brownian motion. So diffusion that change the behavior in different regions. And therefore, I looked at the problem of what happens for this kind of processes. Do we have the same kind of convergence to local time as for Brownian motion? Because they are basically Brownian motions. They are basically Brownian motion, except that either they have a different volatility in one semi-axis and another in the other, or they have a certain probability to go on the left and on the right very early at the point, or here the weird behavior is the stickiness at 0. And so for Brownian motion, it is known, so we use the techniques of Jacob and the results for Jacob, that for Brownian diffusion, like that, then you have optimal rate of convergence when you take a scaling which is just the square root of n, for this kind of nice function that are bounded here with some nice integrability and which are exponentially bounded for the increments in such a way that if you think of Brownian motion, then it is Gaussian and then you can still integrate. And then you would have that those statistics will converge to the local time times a constant, which is nothing else that the constant which makes that you imagine as if the process will start from its stationary measure, which is not a distribution, like the Lebesgue measure for Brownian motion. And then you look at how your process at time 1 would look around in the space. So you imagine as if it would go in all the space, and then you will see what happens with this function. And that's the role. And then, as I told you before, the rate of convergence of n to the 1/4 with the limit stable in low to the local time times the random variable. So it will be a Brownian motion at the time, the square root of the local time, actually, but we are at fixed time, so we consider random variable. So stable in low to a quantity which has a variance which depends, or a random variable which has a variance which depends on the local time of the process itself. So that's a complicated expression, but we wanted to see what happens for this kind of statistics for sticky Brownian motion. And the baby step we found is to consider the number of crossing, what happens. And we already have seen that the number of crossing cannot have the same convergence because of the result of Efimenko and Portenko. And yet we could at least, and this is the result that I presented last year for some people who were in the audience at the time. So we could prove that for a function which is integrable and bounded, so a baby step as well, which is not the number of crossing statistics, you can isolate the behavior at 0, and you will get the convergence of the statistics to the local time times a constant. Same reasoning as before, that you let the process go through everywhere. And here, for sticky Brownian motion, the stationary measure is the Lebesgue measure, so it is this one. And therefore, this means that if you do not look precisely at 0, but you look only around, then this is just as Brownian motion, which is what we expect. And we do not have the stickiness, we have nothing. But then what happens at 0? Well, at 0, we have to look at occupation time then. So we do not have, we can look at approximation of local time. We know it's proportional to local time, but then we can look at occupation time. So we have occupation time for all intervals, but what matters to us is the degenerate interval and those intervals for the occupation time and the convergence, the standard convergence that you would expect. So that's nothing special here. But this allows to do what I told you, and now we make a break and we look at what can be an estimator of thanks to these two results before to pass to the number of crossing and trying to understand how to generalize the general case for different statistics. So an estimator would be just that. Now you can ask a lot of questions like, yeah, okay, but when you measure, when you look at the process and you won't get exactly 0 because you may have an error and so on. Okay, for the moment, let's assume that everything works ideally fine. And then actually your process, the number of 0, so the set of 0 of your process, it's a fat Cantor set. It is basically a Cantor set with positive Lebesgue measure. So you will find points with your process stays at 0. And so theoretically, so this is theoretically, you can provide many estimators, for instance, this one with different scalings. So, okay, so this is an example of estimator, and that's just the basic idea that I keep telling. But what interests me is the local time approximation. So we found out an interesting fact. It is consistent, yeah, of course. The results that we have, they prove consistency. But we do not have yet the rate of convergence. That's why we want to look at the question, the general, so the rate of convergence question, and also to the general statistics that I showed you before. Okay, and also ask yourself for the optimality as well. Because we know that for the optimal scaling for a Brownian motion is the square root of n, but for sticky Brownian motion it seems to be different. It can be for the approximation result that we use for simulation, but could also be a reason of math, and we are trying to explore that. And indeed, one step is this. So one step is this. We consider different crossing. Because we know that the number of crossing statistic would converge to without rescaling to a discrete random variable. And indeed, we count the number of zeros, basically, or number of crossing, which tells you that you have crossed 0 and you have spent some time there. And so there you see that we can consider different scaling, and we have a result which is amusing for us. That's which is an application of what we showed before, which is that if we add to the number of crossing, which is the standard one, the case in which you allow the extreme of 2 consecutive observations to be 0, one of the 2 or both, then you change the behavior because the occupation time comes into play. The occupation times comes into play because you look at, for instance, when here you have one of the 2 is 0, or both is 0. And when here you look when both is 0, then it is the occupation time which is the best one, which is the fastest one that goes. And here you see that, so that's not the right, but yeah. So here it is. So this rescaling for Brownian motion, it is all the same. Well, thanks. The Brownian motion spends 0 time at 0, then it's fine. But so they converge all to the same thing. But for sticky Brownian motion, that's not the case. And indeed, so what we said here, it is here we have occupation time. So here, if we look at the dominant term, would be the dominant term is the one in which both are 0. So here we said that already from Efimenko and Portenko we could expect, but we proved it. We did it with our techniques because it is just an application. That here for sticky Brownian motion, if you divide by any divergent sequence, then the number of crossing goes to 0. Because well, it converges to a random variable, but okay. And then instead, if you consider that the possibility that both consecutive observations are 0, you count the number of times that 2 consecutive observations are 0, then you get the occupation time. You get as if you would just count the number of observations that are 0. And instead, this one is the one which it's weird maybe for us. We can explain it, but it's the one that is said, oh, wait. Now, if we remove the fact that the 2 consecutive observations are 0, but we just take one of the 2 might be 0. So you have one is 0, the other is positive, one is 0, the other is negative, which explains the factor 4. One is 0, the other is positive, one is 0, the other is negative, and then you reverse, so the factor 4 is explained like that. But then if you consider this, then you get convergence to the local time times the same constant that we had before, except for this factor 4. And we didn't like that at first because we wanted to show some sort of continuity in the stickiness. So we wanted to say, okay, if rho goes to 0, then we want to see also in the limit the fact that the limit is 0 is the same for Brownian motion and not different. And instead here, it is hidden in the proof that this is just like that. And so the idea of isolating the 0 that we had for the statistics in which we take just one function, we look at a spot function and a function of the observation precisely. I don't know, I hope it is clear what I mean. So the result I gave you before, we cannot just isolate 0 in the general statistics that we want to consider, which includes the number of crossing. And we have to take into account the behavior at 0, also for sticky. So now it's somehow application and opening and the proof. So I will come back to that later and telling you what I want to do in the next time. So now an idea of the proof just to get the flavor. Probably you are familiar with this kind of objects, but what we look at is that somehow some sort of linearization and then decomposition of looking at martingales. So we go to a case that we know how it converges, and then we would use results which are known like this one, in this case, which tells that you have a certain convergence. So to prove the result that I just showed you before, then you just need to check that given this definition of some quantities which are measurable with respect to the filtration at the given time that you check, then you will see that if you have convergence of the conditional expectation to a random variable, and if the variance somehow converges to 0, then you will get convergence for the known condition statistics that you get. And so the way to prove for this kind of quantities defined as we wish this result is to use the result that I presented you before, that Alexia and I generalized to sticky Brownian motion, and then so I'm not to make you scared, but that's just reminding you what were the results. And then it is pretty easy to check that the variance, the conditional variance goes to 0. That's not a problem. It follows immediately for this. So the key result is the one that that we proved there. But then, well, right now we have somehow the idea that if we go back to the estimation problem for applying the result to estimation problem of stickiness parameter, then we can do for sticky Brownian motion, but we cannot do for sticky reflected. Because sticky reflected, the crossing is not a crossing. You cannot cross a 0. But then we can consider somehow the number of bouncing. And the fact that the occupation time at 0 is gives you a convergence of the to the occupation time, and so the local time. And the fact that the astonishing to say result of not dependence on the stickiness for the case in which only one of the two consecutive observation is 0, this allows you to get also estimator starting from bouncing of the reflected Brownian motion, because this is not a statistic. If you look at a bounce, we mean that you have the process, it is positive at before and after the time, but in the middle it touches 0. So you have something like that, it's a bounce. And this one is basically a crossing for a sticky Brownian motion. And if you think of sticky reflected Brownian motion as the absolute value of a sticky Brownian motion, then you would have that actually you had a cross or you had a bounce for sticky Brownian motion. So we can obtain the same result of convergence for the bouncing of sticky Brownian motion, and then we can go to proving the same result for bouncing of sticky reflected Brownian motion. And this tells that we can construct difference estimator. We just count the number of 0, the number of two consecutive 0, or the number of one is 0 and the other is not 0. So these are the consistent estimator condition on the fact that, of course, you reach 0. If you don't reach 0 in any case, it's a conditional convergence, but okay. And this is all the application I want to show. And actually, I'm gonna finish with this slide. This is not the last, but the previous last. So all the results we showed, they work for sticky diffusion. And the results, sticky diffusion, but not sticky reflected. The results on bouncing were for sticky reflected. And what we just showed, it is that, of course, this result cannot hold for sticky diffusions, but not in the way that it contains the number of crossing. But it may hold with certain assumption on F. So I did consider different kind of singular diffusion, and I proved this result. And for sticky, we are trying to find the right formulation. And the difference is that you cannot isolate the 0. And we have to look at the different properties and different ways on how to do. So I decided to make a reference, not for all the work I cited, but at least for the one on local time approximation, to show you that it is an old problem, but also very recent. And so thank you very much.
Okay, let's thank the speaker again. Take questions. We have time for more than a few questions. Yes.
So the concept of local is in fact otherwise because nothing is a problem. And some of these assertions, make sense to ask them for classes of functions, irregular functions. So we have some work with Perturbed where we look at this for classes of rough functions, which include sample paths of fractional motion. And we can make sense of this. You can define local time along with sequences of time partitions. Here we use the uniform partition, but something else. And then you can show, you can estimate for a given class of functions, this local path, for example, get results of this type. So the techniques have nothing to do with some of the Gaussian techniques used here, but then they apply to fractional Brownian motions and some other Gaussian processes. If you can make statements about path regularities, which one it's a different dimension.
Yeah.
And then it's one remark is some of the statistics you find are invariant under time change. If you change the steps in the calculation.
Yeah.
So for those ones, you get maybe simpler proofs. I don't know if there is, but you could derive the proof from the Brownian because you're processing the time change on.
Indeed. So
Get proofs. So then you have a quick explanation for why you get this
indeed. So indeed, that's exactly the path that we're going to take. So that was just an example in order to put the hands on and work. So the idea is, let's go through looking, okay, that's a specific class of function. And indeed, I know the work you're talking about. I didn't cite all the possible results. But at least in this case that we look at very well, the idea is to think of one-dimensional diffusion indeed as we said at the beginning. So Brownian time change, Brownian motion time change, and scale function. And what we noticed already is that the properties that we get. So the most difficult part is the speed of convergence, yes, which is the subtle one. But at least for the convergence, then one could approach this through this kind of representation. We have not done that yet, but I think there was a work also of Jacob, which was available in 2017, which would go through somehow that direction, and try somehow to give the convergence result without passing through the analysis of the explicit densities of the process or all the properties that we look at. Because what I didn't say here is that all the results that we give, they go through study of the semigroup of the process and properties of the semigroup of the process, bounds, for instance, and stuff, in such a way that we can deal with the part converges to the local time and another one which doesn't, and go through martingale results and so on. But then, through the analysis of Brownian time change and scale function, one can see the properties that one needs through that bias and decide, for instance, which results can be extended and which cannot in this case, but then one can also look at other cases. So thank you for your remark and also for your question.
Thank you. Take the next question. If not, I have a question. Okay. Yeah. Can you study with limiting parameter stickiness parameter?
Yes, we wanted to, so we didn't. This is a work which goes on since some time. All the time we stop and we do something else. But indeed, we wanted to analyze the random variable to see what happens and to see if we can say something more, in the sense that somehow, if we look, somehow we count the zeros. And in some sort, there's a consecutive zero. And in some way, we hope that we can give a more explicit expression, or at least show what it looks like. But we didn't go further very much in this direction. So there is the intention to, but we didn't.
Also, instead of looking at something, a single process, Brownian motion, or sticky Brownian motion, take a sequence of random walks that are diffused with scale, and you sample them, and you take amplitude. Have people looked at this? And Is it expected to have the same limit law or?
So it depends on the properties of your random variable, you say, but yes, there are people looking at this kind of approaches. Well, the thing that looks most like that is when you look at, or not say something, so the most similar thing I would say is when you look at U statistics and different scaling, and then you have properties on the variables that you look at, and through these properties, then you get limits. So there is a huge literature about this kind of process, and indeed, for instance, there is also literature which looks at U statistics for semi-martingales, for instance, in which the observation that you get are semi-martingale. So I think this is the direction you mentioned somehow. But yeah.
Next question.
Time change of Brownian motion. Every diffusion can be constructed via Brownian motion after scaling and change transformation of time. In some statistics, times are k over n. But if you return back to original Brownian motion, the times will be random. And this is a different story.
Yes, but what I'm saying, the natural thing you would do, if I have to estimate this along path, I would look at heating times on the grid, not fixed times. So if you use heating times on the grid, then actually, first of all, the scaling is irrelevant, you don't care.
Yes.
And then you get an exact, you get an improved convergence for the norm. So this in paper,
What depends on what you observe. If you observe process during, say, a or anything, it's not for it. If you observe all trajectory, that's very different.
So if I may intervene, that's anyway a different question. I mean, it depends on what you observe. So if, for instance, you have observation of, I don't know, if you have observation from the market and you look at precise times, and your question is looking at times with the time step, which is that. From the probabilistic point of view, then yeah, of course, it's very interesting to look at other properties like heating levels and stuff like that, of course.
Any other questions? I just have one. So the Pesker and Engelbert paper, if I remember correctly, they show that there's a joint weak solution, right, and no strong solution, and that verifies Skorhod's conjecture entirely. Is that?
I didn't understand which.
So from what I understand, when you cited the Pesker and Engelbert paper,
Yeah.
right, from what I recall, they actually prove Skorhod's conjecture completely.
Yes.
Right.
Yeah,
Okay. They prove that it's a joint. They prove a joint weak solution, and then that there's no strong
Which is not
solution.
Yeah.
wrong.
Yeah. I didn't know if what you said in the beginning, I didn't quite understand if you said that they proved the conjecture or not.
Oh, I did say that they proved that there was no strong solution, indeed.
Okay.
Yes, I remember that.
Yeah. Okay.
Yes.
Okay. Thank you.
I only said that they prove yeah.
Thank you. So any other questions? Okay, thank you for a great talk. Thank you.